Okay, I want to include some video on gases and gas stoichiometry. One of the things that you need to remember is that all gas molecules are very small. They're so small that the molar mass of the gas does not affect its volume. So the more moles of gas you have, the bigger the volume will be. Fewer moles, the smaller the volume will be. And it has really nothing to do with the actual formula of the gas itself. So it's important to remember that all gases have a volume of 22.4 liters per mole at STP, which is 273 Kelvin in 1 atmosphere. So it doesn't matter if the gas is oxygen, nitrogen, ammonia, hydrochloric acid. At 273 in 1 atmosphere, 1 mole will always equal 22.4 liters. This makes it kind of handy because if a gas reaction occurs without a temperature change, the coefficients in the balanced equation may be used to represent the volume. For example, 2 moles of hydrogen gas plus 1 mole of oxygen gas makes 2 moles of water. So, if you know how many liters of hydrogen gas you have, you can figure out pretty easily how many liters of oxygen you need to completely react it. So how many liters of hydrogen are required to react with 6 liters of O2? Well, here's the number we were given. That's the number we start with. Well, for every mole of O2, we need 2 liters of hydrogen. For every liter of oxygen, we need 2 liters of hydrogen. So, 1 liter of O2 requires 2 liters of hydrogen. Look, liters of O2 cancel. 6 times 2 equals 12 liters of hydrogen gas. So gases are your friends. Let's do something a little more complicated. This is a typical example of a gas stoichiometry problem. To calculate the volume of oxygen produced at 1 atmosphere and 25 degrees C by the complete decomposition of 10.6 grams of potassium chlorate. Now, we're given as a starting material 10.6 grams of potassium chlorate. I know it says 1 atmosphere and 25 degrees C, but those are the pressure and temperatures you're going to use later to convert moles of oxygen produced to gas. So we start with 10.6 grams of KClO3, potassium chlorate. Now, we're doing stoichiometry problems. If you got grams, you got to change grams to moles. So there's always this grams to moles step. And that's what we're doing here. And so we get the molar mass potassium, chlorine, and 3 oxygens, add them all up. It comes to 122.6 grams per mole of KClO3. Now, we've got to go from moles of the first thing to moles of the second thing. So we know that we've got moles of potassium chlorate here. So 2 moles potassium chlorate give us 3 moles of O2. So from here, we know that we can figure out the moles of oxygen. And that's the first thing we need to find. Let's cancel units, make sure it's going to work. Grams cancel, moles of KClO3 cancel, moles of KClO3 cancel. I'm left with moles of oxygen. So, that comes to, we're at STP. This makes it easy. If we're at STP, I can just change this. I just put another step here. Because if we're at STP, 1 mole of oxygen equals 22.4 liters of gas. Now we just multiply it all the way across, and we should get 3.13 liters. This mole cancels this mole. So 10.6 divided by 122.6 times 3 divided by 2 times 22.4 equals 3.13 liters of O2. Let's take a look at another example. Calculate the volume of hydrogen produced at 1.5 atmospheres and 19 degrees C. Notice, this is not at STP. So we'll have to use the ideal gas law to calculate the final volume of hydrogen. We're reacting 26.5 grams of zinc with excess HCl using this equation. Zinc plus 2 hydrochloric acid yields zinc chloride and hydrogen gas. Well, just like before, we start with the 26.5 grams of zinc. We then go from grams to moles, right here, and then we go from moles to moles. So to get moles, we divide by the molar mass of zinc, which is 65.38 grams per mole of zinc. We use 1 mole of zinc for every mole of hydrogen. How do I know? Because that's in the equation. 1 mole and 1 mole. Let's cancel those bad boys out. Get rid of these things. So now I know how many moles of hydrogen that is. So 26.5 grams of zinc will make 405 moles of hydrogen gas. Now we can't stop there because it's asking us for the volume. This is why it's important to understand what you're looking for. So I can use the ideal gas law. PV over NT equals PV over NT. I then substitute in what I know. The pressure, 1.5 atmospheres. The temperature is 19 degrees C or 292 degrees Kelvin. And the number of moles is 0.405. The volume is what we're looking for, so we should have everything but that V filled in. Then over on the other side of the equation, we put in standard temperature and pressure. 1 atmosphere, 22.4 liters per mole, 1 mole, 273 Kelvin. Now, if I wanted to, I could say this equals 0.0852 atmosphere liters per mole Kelvin, but it's always easier for me this way. This is the way I've taught you to do it. This is the way I prefer you to do it. However you do it this way, I'll figure it out. It's not that difficult. So then we cancel units, do some algebra, and we find that V is going to be equal to 22.4 liters times 0.405 times 292 divided by 1.5 and 273. 273. L units cancel except for the liters, and since I'm looking for a volume, that seems to make sense. And then once we pick up the calculator and do the algebra, V equals 6.47 liters. So, that's gas stoichiometry. If you got any questions, shoot me an email.